All right, guys, I'm going to try to get through this lesson. Obviously, I have an upper respiratory infection, which is why I'm not here, but I didn't want to get behind since we will be running out of days due to finals. So I'm going to try to get through at least some of this presentation for you. So this chapter has to do with energy. Energy is the capacity to do work, to move against an opposing force. Energy is a tricky subject because it's not like something we can tangibly or physically see. All right, so it's hard to measure these things like potential and kinetic energy. So potential energy is the ability to do work generally based on its position or its stored energy within chemical bonds. Kinetic energy is energy in motion. So it is that usually what we do is convert our potential energy to kinetic energy. And so like with the yo-yo, as the yo-yo is up in your hand, it has that potential energy of falling down due to gravity. As it falls down, it's going to move and exchange the potential energy into kinetic energy. When it hits the bottom, that kinetic energy is going to have enough momentum then to bounce and oppose gravity and go back up into your hand. And this kinetic and potential energy conversion will keep going. And of course, you have to move your hand. If your hand's still on a yo-yo, it just dies. So you're taking the energy that's stored in your hand and you are transferring it to the yo-yo. So again, the first law of thermodynamics says energy cannot be created or destroyed, only transformed. And this is what we're doing. We're transforming energy from one type to another. So this is where that first law is. We can talk about, and we're going to get to photosynthesis and cell respiration next semester. Photosynthesis is great for showing you the types of energy here. We have the sun. The sun has huge amounts of potential in kinetic energy, the kinetic energy being the photons of light that's traveling to the plant. As that solar energy goes to the plant is then going to convert that energy into potential energy, in that it's going to take carbon dioxide and water and we're going to put that molecule together with that solar energy or kinetic energy into bonds within the carbon molecules, which we then know because we've talked about how sugar is energy. So we're not just making energy with sugar, we're converting that solar or kinetic energy into potential energy during photosynthesis. So our car does the same thing. Our gasoline, this is octane, which has 8 carbon molecules. So we have 8 carbon-carbon bonds, actually 7 carbon-carbon bonds here. And what we're going to do is we're going to use those carbon and oxygen. We have carbon and hydrogen here and oxygen here. We're going to use that oxygen to burn our gasoline, and that internal combustion engine will then drive and move. So that's potential energy will move the car. So we're converting our potential energy into kinetic energy. And our waste product then is, notice how the molecules are much more simpler. We don't have any carbon-carbon bonds anymore. We have carbon dioxide and water. We can say the same thing here for cellular respiration. Looks very similar. We have that glucose those plants made for us. We're going to use oxygen to burn the glucose. When we do that, we're going to make ATP. With that ATP, we are then going to make carbon dioxide and water. Now, do notice in both of these equations, we're not converting 100%. And that was one of your questions in your guided reading. We're not converting 100% of that energy into kinetic energy. Some of it is lost as heat. Notice here, heat. So we're not able to convert all of the potential energy into kinetic energy without losing some of that. We're going to lose it as in heat, and we're also going to lose it as in in entropy. And I'm going to talk about entropy. So thermodynamics is the transfer of, like I said, energy is never complete. Some of it is always lost. So even when we transfer from a warmer object to a cooler object, all of it's not going to go into it. We're going to lose some to the surroundings. The second law of thermodynamics explains what is observed when energy is transferred and why the reactions occur spontaneously or not. Okay, so if we start with coal, coal has this potential energy. Now we know coal won't just spontaneously catch on fire. We have to add flame. Once we add a flame to it, it will then go spontaneously. We will convert all that potential energy to kinetic energy until we're out of coal. All right. So coal, we know, is a very ordered substance. When we break that coal down, it's being converted to carbon dioxide and water. Now those gases are going to be distributed randomly, very unorganized. And this loss of order is called entropy. So coal does not spontaneously reform from ashes. So the question is, well, why can't I take the ashes and make coal back? Well, I can't do that because, for one, I lost some of that substance in that chemical reaction. And for two, ash is very disorganized and coal is organized. So we do not spontaneously go from disorganized to organized. We have to put in energy to organize things, to make things more complex. So the second law of thermodynamics describes how energy is transferred, and it states that when energy is transferred, it always results in a greater amount of disorder in the universe. We call this entropy. So entropy is the measure of disorder. Entropy is one of my favorite thermodynamic laws because it explains so much, especially about how your room gets always, you should notice that your bedrooms always get so messy and it seems like it was very effortless, but yet for you to clean it, it takes effort. And that is all explained by the second law of thermodynamics. So entropy goes up with disorder. A messy room has high entropy. A clean room has low entropy. So which room condition is more like our universe? Well, our universe is very chaotic. It's got a high entropy. High entropy is a natural state of the universe. There is more probable places, and this is all about probability. There's more places. When you think about your room, when it's messy, it's always different, right? Different shirts, different this, different places. But there's really only one way for your room to be clean, to be nice and organized. And so you have one probability, one possible outcome for a clean room. You have many outcomes for a dirty room. And that is why it is more probable to find your room messy versus clean. And this is called entropy, or the second law of thermodynamics. What I'd like you to do now is I would like you to watch this clip on entropy. It will help you understand this particular law. And then you have the rest of the time. I have other movies in Schoology on entropy for you to watch. So right now, what I want the focus of today is for you guys to understand the difference between kinetic and potential energy and the first and second laws of thermodynamics. And that is it for today.